the local change will always be able to take place by any type of a data channel that we open. That's it.
When does the inactivation gate reopen?
Inactivation gates will start to reopen when? -55, because we're back into their threshold, okay? With the disclaimers that it's a bit more complex, but the basic idea. The population will start, okay? When will they finish and complete the reopening?
-7.
Anyone? I don't think we even talked about that, right? But it's going to be around like lower, it's not exactly at the bottom of the undershoot, that's the bottom of the potassium, but since they and the potassium kind of like the same pace, it's around that area. But the important thing, they're going to start opening at -55, which is also helping the shift between one period and the next. Which period and which is the next? Between the absolute and the relative factor period. Because until they start open, they're not responsive as channels. When they start opening, as a population, we start to have some sort of response. Yes.
Kind of like in the same vein, I saw like a couple different like diagrams of this, I guess, between the book and the points and everything. So I was wondering exactly like where the absolute refractory period starts and stops in the relative.
It starts whenever we started to stimulate, because at that point we cannot stimulate it again. Okay, they are stimulated right now. So once they are open, once the channels, the active gates are open, the inactivation gates are still open, that's the time when we have the positive feedback chain. You cannot stimulate that channel again because it's already stimulated. It's doing its job, right? Another stimulus will not have any effect. Okay?
Could you show on the like graph
Yeah.
real quick? Sorry.
So this is -17, I went up. -17, went up and like this. Okay? I stimulated right here. Local change, I reach -55 here. Positive feedback chain, right? So absolute means that when they are not responsive anymore. So they're not responsive here, right? Because they're open. It's like I would ask, okay, when can I again allow the students to go while the students are going? It's to go through this door. So this is already the absolute refractory period once we start. Okay, they're not responsive. But the main issue is that once they're here, okay, now the channel is closed. So now the channel is hypothetically can be reopened again, but it cannot because it's unresponsive. Why? Because which gates are closed? Here, +30, the inactivation gates, right? And we need to bring the channel back into its original state, that the inactivation gates are open so a stimulus can work. Because a stimulus works on the activation gates, it needs to open them. And that's great. But if the inactivation gate is still blocked, then activation gate opening up will not help. Actually, the activation gate is open here, right? And it will continue to be open until -55. So stimulus will not do anything. Activation gate is already open. But it doesn't matter. The inactivation gates are closed, so all the way until -55, until this point, from here to here. Let's say this is -5. Okay, -55. All this time frame, that's the absolute. Once the inactivation gate started to get reopened, this is when we start with the relative refractory period until everything is being completely reset back to -1. Potentials.
In a resting cell, without it being stimulated, if you change the concentration of sodium either in or out of it, is that going to hyperpolarize or depolarize it or not, just because it's not the membrane isn't permeable?
So because it's permeable, you're not going to really have a real change. Now, I'm not saying that you have zero impact, but as we discussed, right, remember the sand and the non-sand and all of this, if you add actually inside, it will have an impact. But if you add something or remove some of it outside, the impact is going to be minute, almost meaningless. The impact will not, and since there is no movement because it's not so permeable, then you're not going to make a change. That's back to the child who was eating the sodium tablets, right? It's just not have enough because of the resting. Now, what did you change when you did add sodium to the outside? Concentration gradient. You change the driving force. You change the motivation, if you will, of sodium to go in. Motivation is not enough. You need a door, and the doors are not there, not enough. So you have sodium potassium pump. So when would it have an effect? What will it have an effect on eating the tablets? So we said concentration gradient. How will that affect the membrane? In what case it will affect the membrane potential? If we do stimulate the membrane, and that's back to the practice that we did in class when I asked you what happens if you put a cell in two different cells, but then you stimulated the ligand-gated channels, you need to allow now the sodium to move in. So you added sodium outside, more motivation, more driving force. If you do open the gates, yes, you'll depolarize the cell more than it used to.
What brings from the state of hyperpolarization to resting membrane negative state?
What makes it more, how we can hyperpolarize the next one?
How it bring from hyper to those?
Oh, you're talking about the action potential at the end? So, I'm not sure.
It's like, so that curve, it goes down.
So action potential.
Yeah. It
Okay,
goes
so you're
down
asking
below negative 70.
what will bring it back from the negative hyperpolar up to the undershoot back?
Right.
Okay? So we have, remember, the sodium potassium pump that will throw potassium in and sodium out. Okay? But it's not the only thing. Because remember, sodium out more than potassium, that makes things even more negative.
Yeah.
So how come it goes up? Who wants to help me? We talked about at least one mechanism. Yeah, so I have, let's say this is the membrane, I'm inside the cell, PCF is outside, right? We started with many potassium ions, and we lost some, right, because of the action potential and repolarization. So now that we are done with all the gates and everything, there is more potassium than we used to have, right? And potassium is a plus, so that makes the cell negative. So what are we going to do? The astrocytes are going to swallow me, if you will, absorb me, removing some cations from the outside, making the cell less negative. Okay? So the astrocytes, by absorbing, will help the cell go away. At some point, eventually, with the sodium potassium pumps restoring the gradient, will reach everything, will reach back to resting state.
So the undershoot occurs because the potassium channels haven't closed all the way yet. And so
Exactly, they're
slowly-
slow to close, just like they were slow to open up.
And then the reason it can go back up to resting is because of astrocytes absorbing.
And eventually, sodium potassium pump
Right.
reorganizing everything and back to the resting state.
So the sodium potassium pump, is that where on the film would that act?
Sodium potassium pump, anyone can help me? Where does it act? Here. From here to here. Sodium potassium pump never stops working. It's just that at this point, it's not, the leak channels never stop doing what leak channels do. Right? Nobody's saying, oh, action potential, now it's voltage gated channels game, and everyone else, shut up, this is not part of your game, right? They continue to work. The only difference is the impact that they have. If this room has two doors, 1, 2, right? Let's say these are leak channels for potassium or for sodium, right? Just 2 doors. Then when the voltage gated channels open up, imagine how I have 500 doors in between opening up. Those 2 leak channels, or if this is the sodium potassium pump, still work. But now they're in the background because I opened so many channels. So they're just almost meaningless. They have very little impact. But once everything stopped, they again become important, just because they are the only ones around. So the sodium potassium pump works all the time. But at this point, they're coming back to being the only players in the game. They and the potassium leak channels. So we are restoring, again, we're going back to all the reversal potential, resting potential, etc.
So if the nerve is not firing action potentials, does it need the sodium potassium pump cell to maintain the rest of the membrane, or can it just maintain it with?
It has to have it, because if we don't, and I asked you a question about this in one of the, I don't remember the study guide, the practice question, you have to have, and this is by the way, not just for neurons, but for any cell. In order to get the negative 70 millivolt, you have to have the sodium potassium pump. Because think what happens. If you have a lot of sodium outside and a little bit of sodium inside, sodium wants to get in. And we said we only have very few lead channels, right? But we still have very few lead channels. So if you just give it enough time, sodium will come in slowly, slowly, slowly. At some point, you'll have equal numbers of sodium here compared to the outside. Same thing with potassium. You'll have no gradient, and nobody will want to make. So you have to have the sodium potassium pump to establish and then re-establish the resting membrane potential.
So it actually determines what's in the membrane.
Eat together with the potassium.
So I remember you saying that local potentials happen in many types of cells, not just neurons.
Exactly.
So-
Basically, all, don't want to say all our cells, but almost all our
So
cells.
what would like be the purpose of that for just a regular cell if it's not simply triggering?
We just started to talk about endocrine system, not for the exam, right? We just talked about that. When you telling, when the hypothalamus is sending, remember, signals, hormones are coming eventually, or neurons are going to a place, and they make a change, okay? Those changes, or neurons going to glands, I'll just use glands, not even endocrine glands, okay? So I have a gland here, and that gland, whatever that is, makes something and secretes that something, okay? A digestive gland that makes gastric juices. We'll talk about those, right? So the nervous system will be here to generate local potentials, okay? And those local potentials will be involved in starting a cascade. Because of the local change, right, there will be impacts here. And as a result, that gland will start saying, oh, I need to make this, I need to make that. It cannot continue the action potential. It can't generate action potential. It doesn't need to. Muscles need to. Potential is yes.
So I know we talked about that hyperpolarized involves both the cycle nervous system and also the entrance of fluoride ions. There.
Let's call it the amber shape. I know hyperpolarization is fine, but it's confusing because of the other things.
So with the fluoride ions entering the cell, is that the heating of the place?
No, don't worry about the chloride ions. Don't worry about it. Okay? You think that I remember which question was which number? Yeah, go ahead. 19 is a question about the makeup disease, the trichloride ligand challenge, and post-national, how this makeup disease damages the chloride and potassium ligand including iron receptors, right? So if I have a problem with the chloride and potassium, what am I messing up with? What cannot I generate? I cannot generate IPSPs, right? So now we need to write. So inhibition of the signal is still possible because the sodium potassium ion pump can move potassium ion out of the cells that doesn't work. Depolarization of the membrane will open up the potassium voltage gated channels. There's so much of hyperpolarized that doesn't work. Depolarization doesn't work with potassium. The signal will continue to fire as long as excitatory, right? So if normally you have, let's say this arm is excitatory, right? Working on sodium, and that's saying fire, fire, EPSPs, EPSPs. And this one is typically providing the IPSPs by working on the potassium or chloride channels. If someone just removed my arm, I'm going to over-activate this one. You just provided those positive inputs, but are not able to provide the negative inputs. Okay? Can you give me an example of a case we discussed? Not because of a problem, a mechanical problem with the receptors, but still a problem that will be very similar to that. Problem where we can still send excitatory signals, but we don't generate IPSPs, and as a result, we have an overactive antibody. Exactly, right? In this case, it's the beta nuclei that normally are inhibited by dopamine from neurons coming from the substantia nigra. In this case, it's not an issue of receptors or beta nuclei, but a problem with the neurons, the presynaptic neurons, but it's the same idea. We'll have an overactive one. Synapses. Let's ask questions about synapses if we can, not just potentials. Yes.
So we're just talking about the same as MS, right?
In what sense?
And like the overactivity.
No, so MS will be different. MS, what we're doing, basically, we are damaging our neurons that cannot send signals because of the myelin sheath and what we discussed. We will talk much later, and we'll talk about muscles. In 3 weeks or 2 weeks or so, we'll talk about an autoimmune disease that does affect these kind of things, but nothing else.
This is just going back to action potentials. I don't know if this is something important, but the reason why the channels are, when a voltage comes through the protein, the channel changes three-dimensional conformation, and that's why you have at negative 55 millivolts, the inactivation gate starts closing.
We're talking about that. The
The
depolarization
rising phase.
The activation gates open up.
The inactivation.
Yes.
Okay,
Stop closing, yeah.
So on negative 55 millivolts in the following phase, why wouldn't the three-dimensional conformation, meaning that it is in the exact same state that it was in the rising phase, meaning that it is already,
Because they're slow.
but, okay.
I know what you're saying. I
Yeah.
understand completely. Again, this is, I mentioned the fact, right, that it's a bit more complicated and that there is a difference. There's not one inactivation. There are actually 4 regions that are inactivation gates. So as a total, we just call it one gate for simplicity to make a simplified version of that, simplistic version of that. So think about it as kind of a very complex lock that you have. When you open it, you don't just open one thing. And this is what happens really in a lock, right? You open one tooth, another tooth, another tooth, When you need to, again, reopen them, it's again the same thing all over.
Thank you.
So on the project exam, there was a question about comparing the somatic and autonomic like transmission of neural signals.
Which one is faster?
Yeah.
Okay, anyone? Why the somatic is faster? Yes.
Some of the, there's like, one of them is myelinated, the other one is in 2 parts.
Right? So we have one simple answer, and some of you suggested that, is you have 2 neurons in the autonomic and you have just 1 neuron. That's already, you have a synapse in the middle in the autonomic and no synapse in the somatic, right? So synapse means a bit of delay. So that's one thing, but the main thing is the myelin. That's what I was aiming for. Because the somatic is myelinated, while the autonomic is, half of it is myelinated, right? One thing that you will not find in your book, but just to note, is that the somatic is also more heavily myelinated, so it's a thicker myelin sheath. Don't even remember that for the exam, it wasn't in your assignment. What's faster, parasympathetic or sympathetic? I hear both. Give me some justification for that. Here's a nice synthesis question. Because, first of all, what's the answer? Para or sympathetic?
It's sympathetic,
Why do you think sympathetic?
because everything's localized along the spinal cord and like we have these like short pre-ganglionic
Which
cells.
one is myelinated, the pre or the post?
Yeah, I don't know.
It's a pre, so parasympathetic, right? We'll have the, you just missed the, which one is myelinated, but actually the thinking was right. Why? Because we have the longer part in the parasympathetic is the preganglionic is the longer, right? And since that one is the myelinated one, we'll have a longer mileage of myelinated axon compared to the sympathetic. So the parasympathetic will actually be faster just because you have more mileage of myelinated axon. And this is a good example of a misconception that we think. Why is that a misconception? Can you think about why would you think that a parasympathetic is slow if you didn't know anything about myelin?
Because parasympathetic is rest and digest, and sympathetic.
Parasympathetic is the inhibiting one, right? It's the slowing down everything, will rest and digest, take a nap. They can take a lunch and nap, right? But sympathetic is fight or flight, okay? Digestive system, stimulated or inhibited by the parasympathetic? Stimulated, right? It's the final function, the final event, the final thing that happened that will determine whether it's a fight or flight or rest or digest. But it's not that the parasympathetic inhibits and the sympathetic stimulates. It depends on the target tissue.
Sympathetic not always being excitatory, like it can inhibit
sympathetic will inhibit. Sympathetic will inhibit your digestion. If you're right now eating your lunch and suddenly you realize, oops, tomorrow I have a 253 exam that I completely forgot about, right? Amygdala, anxiety, boom, 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 sending signals to the cerebral cortex, right? You get this, and then you say, I lost my appetite, right? This was inhibition. That's exactly how we inhibit digestion to the will eventually go, it's all from cerebral cortex, but it will go to the sympathetic. To the inhibition. By the way, and I mentioned that just now to in my office, we didn't have a lot of time to discuss, and we just had assigned readings for that, but just to understand the concept of why somatic, sometimes we don't have a reason why, but sometimes there is an advantage actually. In this case, the somatic being faster than autonomic doesn't make sense. Why? Somatic is turning the lights on or turning the lights off, right? Contracting the muscle, not contracting the muscle. Autonomic is never about turning something on or off. It's about the fine tuning. It's about turning it up or turning it down. Okay, and I mentioned just now in my office that you at least know, I know that you're not experiencing that, but you know there used to be those old radios with the volume that was, right, a knob that you could use it, right? How do you either turn it up or turn it down, right? That's exactly what the autonomic nervous system is doing. It's basically just secreting a bit more, secreting a bit less. Turning the heart rate a bit up and then down. So this is fine tuning. We need to be fast, but we don't need to be extremely fast compared to contract your muscle or not, because you need to run away from the tiger in survival. Brain, let's ask questions with brain. Sorry, okay? Yes, so it will go from the brainstem, of course, if, well, yeah, in many cases we'll go to the midbrain, because we're going to train the muscle will go there. But yeah, we go from the lower parts of the brain. If it comes from most of the body, it will go from the spinal cord there. If it comes from your head and neck, it will go directly there. And from there to the thalamus, with the exception of the foot and then from there to the cerebral cortex, if we go to the cerebral cortex. Because again, not just many, but the majority of our inputs will not be to cerebral cortex. I give you the example of pH in your blood and your blood pressure. We will learn a lot about blood pressure. You'll see everything is going to be the medulla, and the medulla is making the decision without you being aware, and it's as now as you're sitting here. It's not aware of that.
I thought that pH and blood pressure went to your visceral cortex.
No, so you are not aware, so not everything goes up to the visceral cortex. I gave the example of the urinary bladder, right? I want to pee, but I'm not aware of that. Not everything goes to the cerebral cortex. You cannot tell me right now, Abby, what your pH in your blood. You cannot tell me what your blood pressure is. You might have some experience. You can guess that. You're not aware of that. The medulla is taking care of that right now because it's so important.
So the hypothalamus and medulla both like control the visceral responses.
Yeah, in a way to think about it, it's kind of the hierarchy looks like this. I would use the heart as an example. So heart, okay, and you have the cardiovascular system, and it goes to the body. Okay, the heart. You didn't learn about heart, but you know the heart is responsible for pumping the blood, right? That's not news. Okay. We have pacemaker cells in the heart. The heart doesn't need anything to turn it on or off. It will never be turned off. Basically, it will always have a pace, and we will send blood to all our tissues, including the lungs, different circulations, etc., etc. But above them, we have, I will just put it here, the medulla oblongata. I'll put a name on it, okay? In the medulla oblongata, we have a cardiovascular center. And if we have an increased blood pressure, because we have receptors in our, don't try to remember, it's not important to remember the details, I'm just giving you an example. We have our large arteries, we have receptors, that if you have higher pressure, they stretch. So they always fire an action potential, remember? Slowly, but then they start pace like that. Those signals will go to the medulla, And the medulla will understand, think about it as an understanding process, because it's still central nervous system, although we're not aware of that, right? It's not consciousness, but we're still aware of that. We'll say too much of a heart, too big of a, too large of a heart, too high, I would say, of a blood pressure, right? We need to bring it down, homeostasis. So it will do many things, we'll learn about them, but what do you think it will do to the heart rate, for example? It will decrease it, that will decrease blood pressure, okay? So now the heart, again, is going to beat without the medulla. But you cannot turn it down. You need for that the autonomic nervous system, and you're going to see stimulations. The medulla oblongata will stimulate the parasympathetic, will inhibit the sympathetic. The details are not important here. So it's kind of like the manager, right? This is the assembly line, and that's the manager, shift manager, right? It comes and say, work slowly at this point. Give me a second. Above the medulla, we have the CEO. That's the boss. That's the big boss. That's the hypothalamus. I'm even going to put here cortex, although it's above, I don't have place, right? So that's the one. So the hypothalamus, for example, although everything is okay and the blood pressure is okay, suddenly I see in my eyes, I walk in nature, and don't think about us walking in nature, we're not in nature, right? Think about a deer, okay? You eat the grass, okay? And suddenly you see something, you don't even know what it is, starting to run towards you, okay? Now you see that, so it's working, and that's involved the cerebral cortex, you're aware of that. As a result, you want to have your heart beat much faster right now because you want to stop eating and you want to start fight or flight. In this case, it's going to be flight. Okay? So, how does it work? The cerebral cortex will talk, EPSPs, IPSPs will talk with the hypothalamus. The hypothalamus, as the big manager, is going to go to the medulla oblongata and say, start to stimulate the heart. It might be that the medulla is not doing anything at this point, and it might be the medulla is working to reduce the heart pressure, but now the hypothalamus, the CEO, is saying, no. We need to work faster now. Why? I make the decisions. Sometimes the hypothalamus will get signals from the cerebral cortex, but sometimes not. Maybe through the amygdala, from emotions that you're not even aware of them. So that's the idea. It's still fine-tuned, right? We did not turn the cardiovascular, the pacemakers on or off. It still works. But that's the idea. Okay? Sympathetic. So parasympathetic is what? Rest. That's the easy one is to think about it. To think about just what's the functional member. And sympathetic? Fight or flight. 2 F's, sometimes known as the 4 F's. You know the 4 F's?
Fight.
Okay. We'll actually talk about this at the end of the semester, and we'll talk about the 4F, and you will see that this is an interesting case because that's the case when the parasympathetic and sympathetic do not actually contradict. They both work towards such an important goal of the next generation. I should erase that, right? Because before I get fired? Okay. There, you have a question?
Yeah, I had a question on the practice exam.
Yeah.
Specifically, it was number 27, and it says a disturbance of posture, muscle tremors at
Damage
rest.
to the basal nuclei,
Yeah.
right? What's the problem with that term? The false part is damage to the basal nuclei. What's the false word? It's a damage to the basal nuclei. Nothing happened to the basal nuclei. The basal nuclei are very happy with what they do. They just do it too much. It's damage to where? Okay?
Thanks.
Very important when you read the exam. I promise you I'm not going to trick you, although you'll think that I'm going to trick you. I'm trying to trick you. But when you read a true-false question, and when I say you read a true-false question, it can be also a multiple choice, but each sentence is a true-false question, right? Remember that a sentence is false even if 90% of it is accurate, but there's something that is false. Okay. Another thing that I wanted to add, because I think Dimitri, you asked me about this, right, about the parentheses? You, I don't remember if it was you or someone else. If I write something, I gave an example, it was, the question we just mentioned was about decreasing the potential, and I wrote in parentheses lower than negative 70 or higher. If I write something like this, don't try to think, oh, maybe that's the false part in parentheses and this is what it's trying. The parentheses are there to explain, because decreasing potential and increasing potential, I used to write those questions and I realized some thought that when I say decreasing, is that decreasing the magnitude, or is that putting it closer to zero or above, positive, negative? It's so confusing, so I just wanted to explain in parentheses to give you an example, okay? So it will never be that the parentheses is a false part to what it describes. This is to help you in that sense. Brain.
What is the relationship between the cerebral cortex, the cerebellum, and the basal nuclei with like balance?
What you need to do is just that the cerebral cortex will be the main one responsible for movement, and we talked about the premotor cortex, right? And the cerebellum as an autopilot, and the basal nuclei with just what we discussed are going to contribute to the plan. You don't need to know more about the details of the interactions between them.
Does the heart send signals to the medulla oblongata and the hypothalamus both all the time, or it's only?
The heart will send signals to the medulla oblongata,
Does it?
not to the hypothalamus. The
Okay.
hypothalamus will get signals from other parts and will send it to the medulla oblongata.
So what would happen if there is damage to the basal nuclei?
That's a good question. What will happen to the damage of basal nuclei? There will be different phenotypes. It will be more about lack of movement rather than too much movement. But again, you do not need to guess that.
Okay.
Could you explain why the effect of somatic fibers is always excitatory and never immediately?
Yeah. So if you remember, this is more about a factual part that we mentioned. So if you remember, I gave you, when we talked about synapses, I told you about when we asked about the impact of the neurotransmitter, and then we asked about the receptor. I gave you actually that example. Acetylcholine, so when we have somatic, right? And this is a skeletal muscle, okay? And this will always be excitatory. It will always be one and only one type of neurotransmitter, which is acetylcholine, and the ligand gated channels for acetylcholine will always be sodium. I briefly mentioned that it's actually also potassium, but potassium doesn't have a real impact, so we just call it sodium. Okay, so this is what we call the neuromuscular junction. We will talk a lot about this when we talk about the muscular system. Right now, this is always excitatory. Okay? While in the other cases, that really depends on, it can be inhibitory and such. So it really depends on the other targets. Somatic, you cannot inhibit. You can either turn it on or not turn it on. That's the idea. Good.
The last question on the practice exam, contralaterality of the brain is achieved mainly by commissure fibers is false.
Mhm.
What is responsible for?
Okay. Let's start first of all about the first part. Contralaterality, we did not cover this in the class, but you should know from this from the lab. Contralaterality, the fact that my left part is controlled and controlling the left hemisphere controlling the right part of my body. I touched my cup. Sensory receptors, right? Action potential going to the spinal cord. Eventually it will reach the right cerebral cortex, primary somatosensory cortex, right? How did you make it from the left to the right? Was this at the cerebral cortex, moving to the left and then it moves to the corpus callosum? What happened? That was a crossing over, that was a cross, right? Or decussation. Where? Depends on the tract. Sometimes it's mainly in the spinal cord. In some cases when it's in the medulla oblongata. But it's before we reach the cortex. In the cortex, we get it. The lateralization is about the fact that our brain, our hemispheres are not symmetrical. Some parts are symmetrical, some are not. And if you do have interaction between them, those, these are the commissural fibers and mainly the corpus callosum.
So is that question more true, not exactly true, but more true if you replace commissural fibers with projection?
No, because it's still not, because it's not between the, it's not inside the brain, but it's before, up to the lower parts of the brain. This is where you crossed over. From then on, it goes from my left part to my left part, my right part to my right part. The crossing over, the contralaterality part, was before this part.
What would make it true, like what?
If I ask you contralaterality in causation in the spine cord, then I would never ask you because you didn't do anything in lecture. This was the last part. The main idea was to make sure that you're not confused. I emphasize this in class to make sure you're not confused between contralaterality and lateralization. It sounds so similar, different things. Lateralization is the idea that one part of the one hemisphere is not identical but different. Some parts are stronger in the left or the right, and some parts just exist only in the left or only in the right. It's the fact that it's asymmetrical serial cortex. That's what we're doing.
So if it was just laterality, would it still not be the commissural fiber? Because about people that didn't have a corpus callosum?
Yeah, because again, it all happens before that. It reaches the signal that reached my left arm to my right hemisphere. It happened before it reached the lower parts of my brain.
So with just laterality, just the differences between the
That's lateralization. I know it sounds similar.
Yeah, yeah.
So you'll still have lateralization even without a corpus callosum because you'll still have, let's say, the Broca's area only on the left side. Okay? But the problem would be with the interaction or with the final function because they don't speak with each other. So that might be like the split brain. Okay? I gave you anyone have a chance to go to the website of the Nobel Prize when I gave you? So it would be an example. Okay. Let's do this. You have only your right hemisphere, okay? When you use that. Imagine you just removed your left hemisphere, okay? What do you see here? What I see here with my right hemisphere, I see a circle, 2 dots of this. Or this one, for example, I see different types of, shapes, okay? I might even, because of memory and everything, I might even see that this is maybe a face even, or this is even the number 4. Now let's switch. It's only the left one. In the left one, you're seeing this is 4, 4 equals 2 times 2. This was a face, a smiley face. You're thinking past, future, much more logic, much more math part that you could do that. Of course, this is very, very, like, crude, if you will, split brain. But that's the idea. You need to speak, each hemisphere needs to speak with the other one. Sensation or brain, whatever works. Yeah.
The sympathetic system, it also has, with its excitatory abilities, it also has some inhibitory abilities as well, right?
The sympathetic, definitely, yes.
So where does that compare and contrast the parasympathetic's abilities to?
Again, the parasympathetic and the sympathetic will always stimulate some organs and inhibit other organs. Now, since they use almost exactly individual neurotransmitters, right? It's true that some, not many, but some sympathetic also secretes at the end, but mostly it's norepinephrine. Okay? That means that norepinephrine needs to inhibit something here and stimulate something there. How does he do it? Because of different receptors. One would be a potassium, norepinephrine ligand-gated channel, and one would be a sodium.
But their job would be the same thing.